So now we're going to talk about how we name compounds. The first thing you're going to have to do is memorize what we talked about earlier, how certain groups have certain charges associated with the ions that they form. All of these two tables right here are showing you the charges of those specific groups. There's a few here that aren't part of those groups that you can still memorize, but for the most part, all of these are in groups. And if they're in groups, then you know what the charge that they'll form will be. These are the ones that you'll have to kind of memorize. Polyatomic ions. So polyatomic ions are ions that are made up of more than one atom. So all of these compounds here, they have covalent bonds within them, because if you look at them, they all are nonmetal with a nonmetal, 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 and if you keep looking, that's what, for the most part, they are. There's some exceptions here, like chromium and oxygen, but for the most part, they're all nonmetals with nonmetals. And they have a charge on them. So it happens in nature where you can have a compound and it won't be neutral whenever it forms. Instead, it'll have a charge. Because it has a charge, it can bond with a metal in order to form an ionic compound. Now, all of these polyatomic ions have certain formulas and certain names. So this acetate name is only for this formula, like they're very specific. So you're going to have to get used to using them, know what their charges are, and it'll definitely help you when you start practicing the naming. So for naming ionic compounds that are monatomic ions, so in other words, you have a singular atom and a singular atom for both of them, what you're going to do is you're going to take the name of the cation, so in this case you have aluminum, and then you're going to take the base name of the anion, you're going to take off the end of it, and you're going to add I to it. So here we have oxygen, and instead of oxygen, you replace that gen at the end with "ide." So now we have aluminum oxide. Here are some more examples. We have sodium. You just take the name of sodium, you take the name of chlorine, you cross the ending out, you add "ide" instead. So we have sodium chloride. Same case here, you have potassium bromide. Now this is a little bit more advanced, so for naming ionic compounds that have polyatomic ions, you will either take the name of the metal, the cation, so for example potassium, and then if it has a polyatomic anion at the end of it, you're just going to take the name of that polyatomic ion and you're going to stick it on there. You don't do anything to the name, you don't change the ending or anything. So that's kind of the easier part. It's just knowing the name to the formula. Here's another example. We have aluminum and carbonate. You don't change the name of carbonate or anything. This example shows you the fact that there's a few, I believe just one or two polyatomic cations. One of those is ammonium. So if you look at all these charges here to the rest of these, they're all negative, but this one's positive. So this one can be the cation. If you have this case, you will still end up changing the name of your monatomic anion to "ide." So this is another version of naming ionic compounds. This is naming whenever you have transition metals. So it's the same naming system, but the difference is in the metal. So you'll have the metal name, and then it will be followed by parentheses and the charge of the cation in Roman numerals inside of the parentheses. And then you'll have the good old regular name of the anion followed by the "ide" ending. So here are two examples. You have iron. Iron's a transition metal. Transition metals, what's special about them, one of the things that's special about them is that they can form different charges. So iron can form iron +2 or it can form +3. So here you have the different versions of it, and you can see that it ends up changing the formula for it as well. So we're going to practice that in a few slides later, but here you have iron 2 versus iron 3 chloride. Last but not least, we have hydrates, naming ionic compounds that are hydrates. Hydrates are ionic compounds that have water molecules as integral components of their crystal. So essentially what happens is you'll have the ionic compound unit, and then it'll have water molecules kind of lodged in there. But this occurs for several different ionic compounds, many different ionic compounds, where you'll have the hydrate version versus the anhydrous version. Anhydrous version means that you don't have water. So here, in order to convert it from hydrate to anhydrous, you can heat it up and kind of dry out all the water. But you can see that it really affects its properties. I mean, the most obvious one is its color. But as far as naming, it's the regular ionic naming, and then the only different part is that you have to account for the water molecules and you have to specifically state how many. In order to state how many, you will use this prefix naming system, which you can see on the slides, but sorry that they're behind my video. But for example, when you have 5 water molecules, the hydrate is what signifies you have water, and then the penta means 5. Whenever you have 10, you will use the prefix deca, and so on. So naming ionic compounds is honestly way more difficult than naming molecular compounds. For molecular compounds, there's pretty much only one way, and that's it. There's no like transition metals, polyatomic ions, hydrates. It's just molecular compounds, and that's it. Now, when you get to organic chemistry, you'll figure out that that's a lie and it's very difficult. So for this class, you don't have to worry about molecular compounds being, naming molecular compounds being that complicated. So we're going to start off by placing the more metallic element on as the first element that we write out. Now, if you noticed earlier, every single ionic compound that we named, we put the metal first. So we're going to do the same thing for molecular compounds. Now, in order to distinguish what element is more metallic, because think about it, we're naming a compound that has 2 nonmetals. So how do we determine what's more metallic if they're nonmetals? So you're going to look at the periodic table. So whatever is farther to the left and to the bottom, so it's to the bottom left of the periodic table, that will be the more metallic element, and that one will go first. The second element, you will change the ending to "ide", and then you'll add prefixes to both the first element and the second element. So let's say we have SO2. We only have 1 sulfur, so you will typically omit mono if it's at the first element. And then we have 2 oxygens, and the prefixes that we use are pretty much the typical prefixes that are used. For example, the hydrates that we were talking about, they're in the book. And then for carbon monoxide, we have 1 carbon. Like I said, we typically omit the mono if it's at the front, in front of the first element. And then for the second element, notice that we're naming oxide, right? So monooxide would be a lot, and chemists are lazy, so they just skip that second O and they make it 1 O. So again, remember, it's prefix, the name of the first element. You don't change any ending on that first element, so sulfur stays the way it is. And then prefix and the name of the second element, you take off the ending and change it to "ide". So we're going to learn about naming acids as well. So there's 2 different types of acids, binary acids and oxyacids. Many of the fruits that you eat, in case you're wondering about like where you see acids very often in nature, all the fruits that you eat that are very citrusy, very sour, those all have citric acid usually, and that's what makes up that sour taste. So the first type of acid that we're going to name is binary acid. Binary acids are the ones that have a hydrogen. So all acids have hydrogen in front of it. That's what's common between them. Now, the difference between them is what is after that H. If whatever is after that H is usually a halogen, that means it's a binary acid. So what you're going to do whenever you name an acid, a binary acid, you're going to replace hydrogen with hydro. So here we have HF, right? Instead of writing out hydrogen fluorine, we're going to replace the hydrogen with hydro. The nonmetal's ending is replaced with ic, so instead of fluorine, we say fluoric. We put it together, so it's hydrofluoric, and then you add acid to the end. The second type of acid is called an oxyacid. Oxyacids will have oxygen in them, and typically what I hope that you'll notice is that these acids have polyatomic ions within them. So remember we talked about polyatomic ions earlier, we talked about acetate. If you go down that list, you'll see nitrate, you'll see nitrite. So you'll see those types of polyatomic ions. These can all form acids. Now, this is the rule for naming those oxyacids. And there's two different avenues that you'll go to. So if the ending of your anion, typically your polyatomic anion, ends with ic, this is what you'll do. So let's say we have H2SO4. SO4 is called sulfate. So what you're going to do is you're going to omit hydrogen. So we cross out hydrogen. This is sulfate, right? Since the ending is 8, we're going to replace that with ic. So here now it's just sulfuric. And then you add acid to the end. Now, if your polyatomic ion ends with ite, you're going to replace that ite with us. So here we have sulfurous, we omit the hydrogen, and then we add acid at the end. So if it ends with ic, if it ends with ate, it turns to ic. If it ends with ite, it turns to us. So we're finally getting to the part where we get to practice all of these rules that we just learned. So first we're going to start with converting name to formula. Both of these are important, both going from name to formula and formula to name. We're going to start off with some ionic compound examples. So here we have iron chloride. This is iron 3 chloride. So once you see that 3, that means that this is a transition metal. When you see that 3, that means that that's the charge on that metal. So automatically we know this is Fe3+. Chloride, we know, forms a -1 charge based off of the periodic table. Halogens form -1 charge. In order to find out what the formula for this is, you need to find out how many you need of each of these in order to cancel each other out electrically. So if you have +3 on one side and you have -1 on the other side, you're going to need to multiply this times 3. Right? So now we have +3 on one side, -3 on the other side. They cancel each other out. And you can also do the little thing where you cross. So this 3 will come down to be chlorine's subscript. And this 1 will come down to be iron's subscript. So you'll get FeCl3. Whichever way you want to think about it, it's fine with me as long as you know how to do it. Okay, so this is an example of a transition metal. This right here is an example of polyatomic, so I'll write polyatomic ions. So we have sodium, that's easy. We know sodium's alkali metal group forms a +1 charge. And then we have carbonate. Now carbonate is a polyatomic ion. This is the formula, and this is the charge. Again, you can do the little cross multiply thing. So for sodium, you will end up having that 2 right there. And for the carbonate, you just have 1. So that's a pretty good example of having polyatomic ions. Here we have another example that's also polyatomic ion. We have magnesium. Magnesium is in group 2, which forms a +2 charge. Hydroxide is a polyatomic ion, forms a -1 charge. Again, cross multiply. It's very easy. So Mg, there will only be one of them. Now, OH, you're going to have 2 of them, but you can't just write OH2. If you write that, you're writing a completely different molecule, which is actually water, which you don't want. So you're going to put this in parentheses, because having 2 OH units is different from OH2. OH2 is water. OH2 parentheses, that means you have 2 separate hydroxides in there. So this would be the formula for magnesium hydroxide. So now we're going to practice going from the name to a formula for molecular compounds. These are very simple and you'll kind of get it right away. So first we're going to write out the symbols and then we'll use those prefixes to determine how many. So here we have sulfur and we have fluoride. This di is telling me I have 2. This tetra is telling me I have 4. And then we'll keep going. There's nothing here, so that means we only have 1 carbon. For oxygen we have tri, so that means 3. Nitrogen and oxygen, there's no prefix here. Pent means we have 5. And then finally we have N and Br. That tri is telling me I have 3. So in this example, we will be going from a formula to a name, and specifically we're working on ionic compounds. So here we have iron, and if you actually begin to notice, recognize that this is a polyatomic ion, and specifically this is carbonate. So we can go outright and already write that this is carbonate. We don't need to write how many, we don't need to write anything at all about that. Now, iron is a transition metal. For transition metals, you do need to write in parentheses what the charge is. So we already know that part of what we write out is going to have to be what the charge was. To figure out what the charge is, that's the tricky part. So we know that we have 2 irons, and then we have 3 carbonates. Each carbonate has a -2 charge. So total, this is a -6 being contributed by the carbonates. We know that when ionic compounds form, they cancel each other out, the positive and the negative. And we know that we have a total of 2 irons. So essentially what we're doing is we're solving for x right here. And we know that for this -6 to cancel out, this side has to be +6. So when we solve for x in that sense, then we have, if you want to set it up in that sense, is what I mean. 6 equals 2x. When you solve for that, x equals 3. So we know that iron is +3. Now, in this next problem, we have copper and hydroxide. So copper is a transition metal. So again, we're going to have to do a very similar setup to what we just did for this iron carbonate. So we're going to find out what this polyatomic name is first, and it's actually hydroxide. So you can go ahead and write that out. And then as for copper, we have to, again, remember to put the charge in the parentheses, and then we have to figure out what that charge was. So we kind of have to go backwards. You always work backwards with these transition metals. So we know that there's 2 hydroxides, each one is -1. So far we have a -2 charge being contributed by this. We know that this has to equal 0. So that must mean that this side is +2. Since we only have 1 copper, unlike earlier where we had 2 irons, we don't have to solve for anything. We automatically know that this copper is +2. So you put a Roman numeral, sorry, my Roman numerals are ugly. You put a Roman numeral 2 in this case. So it's copper 2 hydroxide. And then finally we have a compound that has 2 polyatomic ions. So we have ammonium, right? You see that NH4, and then we have sulfate, which is over here. And this is actually very straightforward. Sulfate. You just take both names. That's it. So that's the good thing about those types of ionic compounds. So finally, we're going to go through some examples of going from a formula to a name of molecular compounds. So here we have bromine and iodine. And we know that we're going to just take the name of the first element, and then we have to change that ending to "ide." So it'll be bromine, and I still haven't added prefixes, and then we have iodide instead of iodine. Now we have 2 bromines, so that's going to mean di, And then we have 4 iodides, so that's tetra. I forgot for a second. Here we have 5 phosphorus, so it is penta. These are very easy in comparison to those ionic. And then we have 8 fluorine, so it's going to be octa. Fluor, oh, fluoride. Here we have nitrogen. Since it's only one, we skip out writing mono in front of it. And then we have 5 oxygen, which is pentaoxide. Now, you could also write this by taking out that double vowel, so you can say pentoxide instead. I'm not really picky about that. Like, there's very few examples. So as long as you know how to name in general. And then finally we have nitrogen tribromide.